All right, in 4C, what we're going to be looking at are savings accounts or possibly loans where instead of having a single amount that's deposited at the beginning, this is like in 4B, what's going to be happening is there are monthly payments, like little installments as the thing goes on. As an example, we're going to do this one here in a second. This guy, Mark, what he wants to do is save up for retirement. So he's not going to put just some big amount of money into the account and let the interest grow on it, which it could be dumb, but that's not like realistically how normal people do this. What he's going to do is choose a smaller amount, like $250, and he's going to put that in the account every month because that's what he can afford each month, and it continues to add the interest, of course, but he's making these reoccurring payments. That's the main theme in this set of notes. There's the other end of this also, like maybe you have a loan. Example is a car loan. A lot of you know what that's like. And every month you've got to make a payment on it, and little by little that payment will, with the interest and all that stuff, is going to pay back the loan that you took out. All right, so the beginning part, problems 1 and 2, this is really just going to give us an idea of like what's the situation and how the numbers interact a little bit. But then it's going to jump into what is the formula. So most of my effort as I go through the video is going to be focused on actually doing some of the problems because this is a very long activity. All right, so the beginning, this situation with Mark, he's going to save up for 25 years, investing $250 every month as it goes along. This was our formula for compound interest. So what we want to do is tie things to this because we did it in 4B, but it's not actually going to be the same formula. So we're just going to highlight some of the parts that are the same and then how it's strikingly different. All right, in this formula, P is going to stand for the principal, and that principal is only deposited once. It's something that we just put into the account at the beginning, and then it just accumulates its interest over time. Okay, that's not going to fit the situation with Mark because Mark is not putting a single payment in at the very beginning and then watching it grow. He's going to be continuously adding $250 every month. So you can probably already see right now that this formula is not really going to work because P in this formula is a one-time deal, and that's totally not what's going on in his situation. All right, so for the next part, well, actually, first what we do here is we define it as an annuity. That's what this is. Whenever you're making like a monthly payment, and that's how things are growing along, then it's actually called annuity. And of course, you can read through all that and get a better idea of what that means. Okay, so question 2, which takes about a page to get through here, is really just breaking down all the calculations to see how complex this stuff is. First, what we need to do is figure out from our APR, annual percentage rate, what the monthly percentage would be. So we said, okay, if it's 6%, let's divide that by 12 and you get 0.5%, 0.5 or 0.005 as the decimal form, and that'll be the number that we'll be using to do different calculations. This part right here is really confusing, but for the numbers to work out in the formula that we see a little bit later, you almost pretend that the first month was the month before you put anything into the account. So your starting balance is 0, you've earned no interest, you then deposited money at the very end of the account, and that's all you've got in there. So this part is always like a really weird one to talk about. It doesn't matter as you go forward with any of the formulas, so don't stress this part. It's just they pretend that you deposit at the end of a month, so nothing, like you have to include that 30 days beforehand and nothing's happening during that time. But again, don't stress about that part. Okay, so the next month though, okay, when everything starts going, we're gonna figure out that 0.5% of the 250, which is $1.25, and he's gonna get that money. Okay, so then that's going to be the interest at the end of the second month, and that's going to get added onto the 250. But at the same time, right, at the same time that that gets added onto the 250, Mark is going to add another 250 of his own money into the account. Okay, so that's this part here. He started with 250 from the previous month. He gained $1.25 for the interest during that month. And then he's going to add on another 250 as his just money that he puts in there. So it brings him to a grand total of $501.25. All right, at the end of the next month, he's going to gain interest on that. So you can multiply that by your 0.5%, which gives you 251. It's going to get added onto that starting balance, but then he is also going to add on another $250, which will get into here. Okay, so hopefully through that you're seeing that there's a whole process because they're gaining interest and then also adding in another 250 every single time. The next couple questions I think are pretty obvious once you see the numbers that are up there, and hopefully you already had that. Then this question here, how many payments would he be making if this went on for 25 years? That'd be 25 times 12, which is 300. So there's a whole bunch of $250 payments that go into this. Okay, so the point of all of that was to get a feel for the complex nature of like how this is all going, all the adding and the multiplying and the repetitiveness. And of course, what we really want to be able to do is just have a nice formula that we can just say, let the payments be 250, let the interest rate be this amount, and how much will I have in the end of 25 years or something. And of course, you know those calculators exist on like Google, and you do them as like loan calculators. Well, here it is. Okay, so everything up to that was just to show you, yeah, this stuff is complex. There's a lot going on. However, it can be summarized as this. All right, now some of the pieces of this do look like the compound interest formula, like right here. All right, that's still the same stuff that we had going on for the compound interest, but then you have these extra little pieces that are in there. All right, this is your payment, which might just get abbreviated as a P, almost like principal, but so you don't have to write as many letters. But you have that being multiplied by this big fraction. The fraction, just, by the way, you don't need to memorize any of these formulas. I'll repeat that, you do not need to memorize any of the formulas. We'll provide them for you. You just need to know how to actually run the calculations with these things. And having a decent calculator is pretty helpful. You don't quite need a graphing calculator, but man, maybe like a calculator that's $20 where you can actually see all the stuff that you're typing in would be fine. We can talk about that stuff later if you want. All right, you've got your APR divided by N. In this case, N is going to be 12, and go ahead and assume that N is 12 throughout the entire worksheet. I don't think we ever changed that on you here. Which means that right here, you can kind of get used to the idea of dividing your percentage by the N value, the 12, sorry. And if that turns out to be a nice looking number, you can always just write that number in, so you're writing less, just do it to the side. You'll see me do that later on. And that number ends up being the same value that's down here. I think everything's there. You like if you don't know if any of the letters stand for, just like read over the stuff, and what I'd like to do is just get into the process of actually working some problems here. All right, so for question number 3, problem number 3, we go back to Mark, and we actually do the real calculation, right? Because you saw about a whole page of repetitiveness and thinking, oh yeah, if we did this 300 times, it's gonna take a while to get there. Well, here it is, and so if you don't like the formula, remember, this is the alternative to doing all of this stuff 300 times. Okay, and understand how nice that is then. All right, so for this, I got everything filled in. There's your percentage, APR divided by the 12. There's your 12 again. There's your 12 again, APR, 25 years. So that's your 300. All right, so usually when I do, oh, there it is right here. When I do these calculations off to the side, I usually just multiply that number and it goes right into the exponent as that number. I'll also just go ahead and divide these, and I'll just write that decimal in there. In fact, here I even took out the plus sign because you're just going to have 1 point, whatever you get based off of that stuff. So that very quickly cleans it up, makes it look less intimidating, and I think easier than to type in. All right, once you are here, you should just type in the top part, figure out what that is, press enter equals, divide it by that number, enter, then multiply it by the 250. So if you don't have a graphing calculator where you can type all the stuff in there, just do the numerator, figure out what it is, make sure you press enter, then divide it by the denominator, then at the end multiply it by your payment. And at the end of all of this, it will accumulate to about $222,000. All right, then what's interesting from that is to figure out, by going through this process, how much money did he actually, oh, I'm getting ahead of myself on that part. Sorry, it's going to come up in a little while. But one of the interesting questions will be to find out how much money did he actually make in interest versus what he put into the account on his own. And it's kind of cool to see the almost like the bonus you get because you had been doing the investing for this. But that's actually for a little bit later. I just got sort of ahead of myself. Question C, what if we change it to 30 years? I forgot, we're starting small here, and the idea is, well, that only changes the exponents. Now we've got 30 multiplied by 12, which is going to give you 360. So you do all the same calculations as I said before, you get that amount. So with an addition of 5 years, sure, you can look at the difference between these two things, and it's about maybe $75,000 to $80,000 different. Though I should mention that a 6% interest rate is super high. You're not going to actually get that much of a difference. But what we do in these activities is we give you rates that are actually like really large compared to what reality is, because it's easier to work with those numbers. Okay, so don't really expect that there's that big difference of 80,000. That's right there. All right, D. One of my less favorite parts to do here is the whole guessing and checking. What if you wanted 450,000 at the end? But to be honest, I made myself go through the process to check all these values on my own until I got to what I wanted. So we knew that 30,000 from the previous problem gives you about 300,000, but I want to get up to 450,000. So I made an estimate to jump all the way up to 50. I thought, that might be about right in comparison to the other numbers, and I ended up being totally like way off and ended up here. So my little arrows mean I need to go up from here. That was too high, so I'm going to go down. So I'm going to split the difference at 40. So 30 at 50, so drop down to 40, and figured out, oh, that's still way too high. Drop that number down. I really didn't want to drop down to 35. If you did 35 as your next increment, that was a really good idea. But I, for some reason, I didn't want to go down to 35. So I tried 38, figured out that was still too high, and eventually figured out that these numbers were right around the answer that we want. So it's somewhere between 36 and 37. The thing is that there is a way that you can get the answer pretty quickly. You're not going to see that much of it in this activity. You're going to be asked other questions for solving, but you're not going to get asked about solving for the time, because the time sits in an exponent position. And to actually solve for that, you need to learn something called logarithms. So we'll do a little bit of that type of problem. They're always going to be guessing and checking, but we'll keep it to a very minimum amount because it is just guessing and checking in reality. All right, so in the last question, I was just talking about solving for time and describing that that's a bit of a complicated thing to do because time is sitting in an exponent position. However, if you think about a lot of these types of questions, usually the time isn't quite the variable. You think about how much time do I have? Like how much time do I have until retirement, or how long do I have until I need to pay off a loan? So the time isn't normally a variable. What could be a variable though is the payment that we're going to be making. Like if I need to pay off a certain loan for a car within 6 years, I know what the value is like that I need to pay. Like in the end, that's the loan that I took out, but what would be the payments? So that's a little bit more of a realistic question. Or if you have a goal in mind as far as how much you want for retirement, I think that's what this question actually is here. Yeah, she has a goal in mind for retirement. Well, what should her payments be if she expects to have a certain interest rate of 3%? Okay, so off to the side here, a little bit of work that I just normally do is I take the percent and divide it by the 12. Hopefully that turns out to be a good decimal, like it doesn't run on forever. If it does go on forever, you might just choose to use the fractions in the problem. All right, but this one does divide out to 0.0025, which is good. The time that she has in mind is 30 years, so 30 times 12 is going to be 360. So both of those numbers can just go into all three of these places. And that way it doesn't look as crazy as the other general formula does. All right, let's see here. Everything in parentheses are just numbers. Just work that out. Figure out the numerator is and divide it by the denominator. Turns out to be $582.74. that is going to get multiplied by your payment and would become whatever you want in the end. So if you just divide the 1.5 million by the 582, it tells you what P is, and in this case it would be $2,574.06 to some degree. Here's the thing, when you do these problems, depending on how many stops you make as you go through the problems and how many times you round off numbers in different places, you can get values that will range in, a difference of a few dollars or so right here. So if you did the calculation, you didn't get exactly that. The difference is when I'm doing the problems, most of the time I'm using the previous answer in my calculator. I don't think I have it around to show you, but like I use the last answer, which might have 10 decimals behind it. So if your answers aren't exactly the same, that's fine. Let's see. Be very careful about how you are typing things in here. Like I was using a graphing calculator, and they're really nice because you can type everything in there. When I first did this, one of my little mistakes is I had the -1 sitting up here with the 360. I forgot to shift over or move over and then put the -1 here, so I was getting bad numbers. Just be real careful about what you are typing into it. Okay, so we just did that. And I don't think there's really anything hard with that, right? You figure out what your numerator is divided by the denominator, and then you just divide that value from it. I mean, that's all my work right there, aside from what I type in the calculator. So it's not too bad. But really all that's happening here, when you divide that number into this guy, you can, because it's a fraction, you can think of it as multiplying the reciprocal of this by that number. Okay, the inverse, like multiplying, dividing, inverse functions, and you can always describe division as the multiplication of the reciprocal of a number. I don't know how much you remember all of those little things there, but here's a formula that actually tells you the payment. Like if you go to Google and you wanted to look up a payment to, like you're doing a house loan, right? You can type in what the cost of the house is. You can type in the interest rate, and you can type in the number of years that you're going to do this, and it tells you what the payment is, right? So that's this formula, and all it really is the same formula that we saw before, except this is upside down. And one other thing I'll say in a minute, this is upside down. We take the reciprocal of the fraction part, and instead of multiplying it by the payment, we multiply it by the final result, and in turn that gives you the payment. Okay, so again, you don't need to memorize any formulas, but I want you to know that the difference between the payment and the figure out the overall value, the end result A value there, is just using a reciprocal for all of that stuff. So it's the same thing upside down. All right, and then for B, that's literally what we do. We do the same problem for 4A, but we have it all flipped over and we do the multiplication there. In a way, it might be a little bit more complicated with a calculator because you've got the heavier calculations on the bottom that you would need to figure out that you then divide into there. So in the other version, I get to do the majority of the calculations, then just divide by a single number, right? And here I got to take that single number and divide it by a calculation. So you got to be careful on how you work with this. If you do have a calculator like a graphing calculator where you can type everything in, this is a great way to do it. But you know what? It's up to you. Practice them, and depending on what tools you have, what calculator you have, you can either do it like 4A or you can use that formula for the B. All right, this is what I was thinking about a little bit earlier with marks, and I didn't realize that we didn't go into that depth. From here, we talk about what the payment is and what the end result is. But behind the scenes, there's an interest rate. And every time you got more money in there, you're gaining a little bit more with the interest. And it's nice to see that by putting it into an account, not just like saving it in some safe in your house or something like that, you actually gain a good amount of money extra. Though our values are all exaggerated because our interest rates are exaggerated here. But for C, how much would she have deposited over the 30 years on her own? Well, you take that monthly payment and you multiply it by the 360 payments. So she ended up putting in $926,000 money that she earned on her own, that she just had. Okay, but remember that with all the interest and stuff, it eventually turned out to be $1.5 million. So if we subtract from the 1.5 million that she actually now has in the account 30 years later, subtract what she put in, the difference is going to turn out to be the interest. So in this case, it looks like she got back more than half of her money in interest by doing it in that fashion versus just like saving it like in a something that doesn't gain interest, which really wouldn't make any sense. All right, one more time, the numbers are exaggerated. Don't get too misled here that, you know, if you're putting money into the account, just a regular savings account, that it's going to gain a lot of money. You do have to invest into things that have higher returns. Basic bank accounts are not going to give you that much money in return. All right, so 5, this is it's a neat problem. It's a bit complicated because the number of steps that you got to go through here, but it's a really neat idea and like how this guy is going to plan for his retirement. Okay, so what Stephen wants to be able to do is retire when he's 65. Somewhere in here it gives me, oh, he's 30 and 65, so 35 years from now. I knew that was coming up at some point. Okay, when he does retire, he's got a certain goal in mind. His goal is not to have a certain amount of money, like an overall amount, but what he wants to be able to do is think about how he can live each month. So his goal for retirement is that he wants to be able to draw $50,000 per year. That's what he wants to be able to do, $50,000 per year. All right, so at the beginning, what we need to do is find out how much money would need to be in an account so that at the end of each year, it produces $50,000. And he can take that $50,000 out and still have in the account the right amount that's going to create another $50,000 for the next year. So we do this real quick calculation of figuring out, and I didn't mention the APR, but it's 4%. We need to figure out 4% of what number is 50,000. How much does he need to have in the account so that when we find 4% of it, we end up with 50,000. There's different ways to set up the problem. You can do like 0.04 times x equals 50. You can just do that one, but I always like doing this like division approach. I can take the 50,000 and if I divide it by 4%, it gets back to what that larger number would have been. You can do that however you want, but I think that's kind of a neat way to backtrack, and we don't normally teach it that way in classes. Okay, so what this tells us is if he wants $50,000 at the end of every year in interest, and this can happen forever, I know that word somewhere in there, forever, he has to end up with that amount when he turns 65. Anything less than that, he can't actually pull $50,000, otherwise this will start to decrease and he'll get less each year out of it. So we need to get to that number. So now we're going to take that number and let that be the A value, the final result in the balance at age 65. That's going to, like as I got it written here, I'm going to be using this formula. All right, so this is that amount of money that he needs to accumulate. We've got the APR over N and everything filled in. All right, so some stuff off to the side here. 4% divided by 12 is going to be 0.03, and it's a repeating 3. What I decided to do was use this number. I wrote it here, use 0.003333. Just felt like as long as I had at least 4 3s in there, I'm going to get pretty darn close to the right numbers that I want. Rounding it to just 2 3s might take your rounding a little bit too far from, like your calculations too far off later. So I just threw a good number of 3s in there, but there isn't any rule of that. All right, from age 30 to 65 is going to be 35 years. So 35 times 12 is 420. All right, then those numbers, you can see that I placed them into all 3 spots so that it wouldn't look as complicated. We went ahead and did the calculation and figured out that his monthly payment needs to be $1,368.13. If you get something a little bit different than that due to the way that you rounded or you use numbers, that would be fine. You shouldn't be, your rounding would be too far if you were anywhere below like 1,360 or too high if you're around like 1,380. Like once you're about $10 off from that amount, that's, you probably did too much rounding, but you should get close to that number. All right, so C, how much money did Stephen deposit in the account? So this goes back to like that last problem. Well, if those were our payments and you multiply it by the 420 payments that he makes, right? 35 years, 12 times a year. This is the amount of money that he would have put into the account. This is what he accumulated. Slide down. This is what he accumulated. And if we take away what he put in on his own, the difference is going to be the interest, the $675,000. Again, the numbers are a little bit exaggerated here, but just get a feel for what these numbers actually mean. All right, so for the rest of the activity, my opinion, I think it's a bit overkill. I think everything that we did through page 5 is the main idea, and I think there's a lot to be taken from it, and that would probably be enough content just to let you practice and to get used to. I mean, that last problem with Stephen was, if you were doing that independently, then there's a lot of thought that goes into it. But we are required to cover a little bit more and just understand. I'm with you. It's a little bit much. So a couple more things here on page 6. The total return formula is a real like tiny one here. Here it is. Look, whenever you see that word relative, and they even underlined it here, which is really cool that they did it. Relative means percentage. We're thinking a percent of another thing. So earlier in the year, we would have done something, and I described the values as being the new value minus the old value divided by the old value. Like you did that for all types of relative change. You do new minus old divided by old. And that's what this is. The new value minus the principal divided by the principal. So these aren't payments now. These are principal amounts. So again, there's been this weird kind of switch in what we're talking about, and you might need to separate some of your thoughts from what happened in the previous pages. Okay, we also have something called the annual return formula. That is the end result divided by the principal raised to the reciprocal of the time minus 1. I'll let you read over what those all represent. In short, though, it's like a summary of what's happened in the problems. But it doesn't really refer to our payment stuff over here. All right, so a little bit of practice here. If you have $8,000 that you put into a bond and it matures 20 years later, you get that amount. Let's talk about your returns. Well, if we take the difference divided by the original amount, that's going to give you a decimal number back. Just multiply by 100 or shift the decimal and you get 56.25%. So that's your total return. You got back an extra 56.25%. The annual return, basically what is the return that you get per year on these things. Just plug all the numbers in and it turns out to be 2.26%. Okay, so that would be like per year, but this is over the 20-year period. All right, then our last few pages here. It's a good idea that we do a little bit of review of B and C because there are some overlaps in it. But again, if you're thinking very hard about section 4C right now, the first couple problems are going to be a little bit hard to do because these are actually referring to 4B. Actually, I had to read this a few times myself to understand where's my payments? What am I doing? Am I paying like monthly each time? And that's not what's happening in 6. You just make an investment of $5,000. It's going to go for 4 years, compounded monthly. So it just goes back to our compound interest formula from 4B, right? So you just put all those numbers in as you did in 4B, you get that result. Next question, really didn't like that one much at all because what they want you to do is use a different percentage, everything else the same though, use a different percentage and still try and get to the same amount that was accumulated with the 3%. But the variable in the problem ends up being time. And again, when time is the exponent, we don't have the techniques in this course to solve and just get an answer. You can only really do like a guess and a check. Now, I put myself through that process. It's a little bit easier with a graphing calculator because you can type in an equation and then just, there's little techniques on it. So it didn't take too long to get there, but it turns out to be about 4.8. I don't like it. I don't like the question a lot because it's just guessing and checking kind of business there. C, calculate the APY for both accounts. I just didn't want to do it. It's like where it was going with that calculation, you can look at that in 4B, but where it's going with that one is getting to this one saying, why are the APYs higher than what the advertised percentages of 3 and 2.5% are? It's because it's compounding. If you're compounding interest, you're going to get more than the than what's advertised for it.